for the formation of salts. Any question up to there? Any question up to there? Any question? So again, I hope you can pick the structural similarities between ranitidine and cimetidine for H2 blocking or for H2 blockade or anti-ulcer activity. The other drug is famotidine. Again, if you look at famotidine, again, the thiazolidine, not the imidazolidine or the furan ring has been replaced with a thiazolidine. That's a thiazolidine. Again, a 5-membered ring. We do not need to retain the imidazolidine, but again, you see that nitrogen, you still have a lone pair of electrons next to the side chain. 1, 2, 3, 4, 5. So this is a drug that I was telling you. If you look at the number of atoms, it's 1 atom, 2 atoms, 3 atoms, 4 atoms, 5 atoms. 5 atoms to get to this terminal nitrogen. So these 5 atoms, 1, 2, 3, 4, 1, 2, 3, 4, 5 to the terminal nitrogen, but it was still found. Famotidine, though it has 5 atoms, not the 4 atoms found in cimetidine, ranitidine, or nazatidine, it was still found to have very good anti-ulcer activity. Again, look at it, drug here, its group here. It has the sulfonyl. This is a sulfonamide group there. This is a sulfonamide group. The sulfonamide group, remember, it's S double bondo. Again, this group, electron withdrawing. The S double bondo. That group will withdraw electrons from the amino group. Will withdraw electrons from the nitrogen. Remember when we were looking at the sulfonamide, we said that sulfonamide group, or that sulfone group, is the one which makes that nitrogen, the hydrogen next to the nitrogen, highly acidic through pull of electrons. That's the same effect here. That this group can be able to pull electrons from that nitrogen, from that, and even from this, that pull of electron, it's felt amongst the whole of this group. And once again, there is a pull of electrons, there is decrease in basicity. And we realize that is one of the characteristics, that these drugs must have much lower basicity. But when you introduce this guanidino moiety, it increases the basicity. So that basicity must be reduced. Here you have the sulfonamide group, the sulfonyl group there, reducing the basicity, but everything else remains the same, with of course the exception that this one, it's a separator, or the spacer, has 5 atoms with retention of activity, and of course the pull of that, the molecules still being polar enough that those that oxygen, all these groups there give it polarity. And again, it has this group here, which again, because of this amino group there, it can allow for formation of salts. It can allow for formation of salt. So we are saying again, it's a thiazole derivative. It's more potent than ranitidine, and therefore more potent than cimetidine. It has no cases of gynecomastia. It is a weak inhibitor, very weak inhibitor of cytochrome B450. So we do not have major drug interactions. Like ranitidine, salts can be easily be prepared from this component, but its absorption is incomplete with only 40 to 50% bioavailability. And that's why more often than not, the more popular drug is ranitidine. Ranitidine is a drug that at one time had really hit the market. Of course, the brand name being Zantac. You know whether you have heard of the drug Zantac. And of course, cimetidine, one of the brand names. There are many brands. That's why I don't like promoting brands. For cimetidine, one of the very popular brands was Tagamet. So you find, so the characteristics are the same, with the exception of what we have said, that famotidine has 5 atoms separating our previous terminal nitrogen from the imidazole ring with retention of activity. And the final one is nizatidine. And if you look at nizatidine, you will see that nizatidine has the same group as found in ranitidine. This is the group we had in ranitidine. So here there is really nothing new. It is only that ranitidine will have a furan ring, whereas nizatidine has a thiazole ring. I think everything else actually is the same. Even this group is as it is in ranitidine, only change the furan ring to a thiazide ring, and again you retain activity. It's also a thiazide derivative similar to ranitidine, and but has more higher bioavailability, 90%, with no androgenic activity or enzyme inhibition. So that is nizatidine, as I have said, very, very close, I believe, very, very close to ranitidine. You can see that is a group. You can see that the group. So the only difference is that ranitidine has a furan ring and nizatidine has a thiazide ring. So therefore, we are saying that these drugs, when you look at them, they're precursor. They will retain some structural resemblance, but of course there will be isosteric replacement. There is a lot of isosteric replacement whereby the imidazole ring can be replaced with a furan ring, can be replaced with a thiazide ring with retention of activity, as long as you do have provision of lone pairs of electrons next to the side chain. Provision of lone pair of electrons next to the side chain, because those are the lone pairs of electrons that, of course, are being withdrawn by the side chain. And those lone pairs of electrons, once they are withdrawn from that nitrogen, you leave the nitrogen positive. You leave the nitrogen positive, so it cannot be protonated, because protonation requires the nitrogen to be highly nucleophilic. You withdraw its electrons, it becomes more positive, the molecule becomes more acidic, less basic, and we promote, as we have said, the teletautomer, which indeed is needed for activity. Any questions before I proceed? Any questions? If no questions, we move on. Thanks. Any questions, class? Take a glass of water. My throat is really dry. Right, I can see you have not asked any question. My throat is a small problem. So if we have understood everything, then we move on to the histamine, that's H2 receptor interaction. Remember, we have the H1 interaction, we have the H2 interaction. So here we are saying we do have cationic histamine binds the receptor via the formation of 3 hydrogen bonds. If you look at the histamine, it has, if you look at this, if you look at the histamine, it has the teletautomer hydrogen, sorry, nitrogen, it has the pi nitrogen, and it has the terminal nitrogen. Now, thank you. The teletautomer nitrogen is usually protonated, it's an NH. So that hydrogen, which is part of the bang the door, bang. That hydrogen, which is part of the nitrogen, because if you look at the nitrogen, it is an NH. That hydrogen can bind the receptor, the H2 receptor, through hydrogen bond. Because you know, when you have a hydrogen attached to a nitrogen, it can bind through hydrogen. Then you also have the nitrogen, which is the pi nitrogen. Even that one finally also binds the receptor through hydrogen bonds. Then you have the final one, the final protonated or cationic nitrogen of histamine, which is usually NH3+. That will bind the receptor through ionic bonds. Because it's cationic, it will go for the negatively charged portions of the receptor and therefore interact with ionic bonds. And then the middle, where you have the CH2, that area can interact with the receptor through hydrophobic bonds. So we are just saying that the histamine can interact with the receptor through different areas, and we are saying the cationic histamine binds the receptor via the formation of 3 hydrogen bonds. That's a cationic histamine. We are calling it cationic because it's already protonated. The cationic nitrogen and the telenitrogen of the imidazoline are hydrogen donors, and the pi nitrogen acts as a proton acceptor. So if you look at draw the structure of histamine, and we are saying you have that the first nitrogen, the nitrogen number 1 is an NH. It will bind with the receptor through hydrogen bonds, whereas whereby it's like it's the one which is donating the hydrogen. Then there is the pi nitrogen that has a lone pair of electrons. It will bind with hydrogen through hydrogen bonds, like it is the one which is donating the lone pairs. And then, of course, you do have the cationic nitrogen itself. Again, it will be like it's the one which, again, donating the hydrogen and you bind through hydrogen bonds. So that's why we are saying it can bind through to the 3 hydrogen bonds, the nitrogen, the imidazoline, the pi nitrogen, and also the cationic nitrogen. Participation of the ammonium group in the hydrogen bonding inevitably leads to a decrease of the positive charge on the ammonium group. That just was found as a fact, that when the ammonium group, that is the NH3 ion, the ammonium group is the protonated ammonium group, and the protonated amino group, when it binds the receptor, that decreases the positive charge on the ammonium group. Increasing positive charge induces atomeric change in the imidazoline, resulting in a stronger binding of the pi nitrogen and proton release by the telenitrogen. We're only saying when the ammonium group binds the receptor, it induces some change only to make the bonding even more stronger. So the whole of that explanation is just explaining that when the ammonium group binds the receptor, that it's like it leads to a conformational change, and that conformational change within the molecule even makes that molecule, that is the histamine molecule, bind the receptor more firmly. Remember, we want it to bind the receptor well to trigger the histamine, to trigger the acid release. So we are only looking at how histamine interacts with the receptor. It interacts through hydrogen bonds. The net result is a proton shift at the receptor surface, which is believed to trigger the H2. The mechanism calls for the presence of a hydrogen atom in the position 1 of histamine. That's why we are saying you always must have the teletautomer, and recall that 1-methylhistamine is unable to stimulate the receptor. So we are only saying that these drugs must have must have a hydrogen at the teletotomer. Must have a hydrogen at the teletotomer. They must also have a certain shape. They must also, remember we did mention that they must also have some specific stereochemistry for them to be able to bind the receptor. And that is why we said, if you put either alpha or beta methyl group, this histamine will not be able to form the trans conformer. And it is the trans conformer which is supposed to bind the receptor. All this we had discussed earlier. So that is just a reminder of what is happening. SAR of the H2 blockers, and we're only going to go through what we have already said. And the first point we are saying is that the imidazoline is not required for activity, because if it was required, then ranitidine, yes, niko kwa class sawa sawa. So we are saying the imidazoline is not required for activity, but if it is present, then it must have the teletotomer. If present, the teletotomer must be the one which is in existence. Other aromatic rings should contain N or pi electrons next to the side chains for H2 blockade. Imidazoline replaced by various nitrogen-containing heterocyclic rings to optimize the activity. So we have seen that the imidazole ring, it can be replaced by furan ring, it can be replaced by thiazole ring with retention of activity. So out of which the furan found in anitidine and thiazole found in zatidine showed good activity. Substitution of the dimethyl amino methyl. So you can also have this we looked at. You can have a dimethyl amino group in anitidine and zatidine, or the amidine group in famotidine groups on ring showed better activity. These are just the groups. In place of the methyl group that was found in imidazole, you find other rings, other groups, like the dimethyl amino group, which was found in anitidine and zatidine, or the amidine group, which was found in famotidine. Again, were found that they produced molecules with quite good activity. So those that was done. Some of these things, remember, they are done during the clinical trials, during the clinical trials, and they put to see which group will be responsible for maximum activity. And it has done what it had done. So we are looking at the SAR.